Okay, voltage, the unit of voltage is volts. Current, the unit of current is amps, amperes. Resistance, the unit of resistance is ohms. P is power, the unit is watts. For those who are not very good in algebra or not having much experience, you can use this chart to find, for example, if you hide the V, then you got I times R. Or if you want to find out what I is, you block I and you see that's V over R. If you want to find out what R is, you see that it's V over I. So the power is voltage times current, or since voltage equals IR, is I squared R. Example, here's an example. A coil with 1 meter length per turn and 2000 turns carrying 1 amp in each turn. The resistance of 1 millimeter diameter wire is 20 ohms per kilometer. Calculate the power consumption and the power supply required. So the total length of the coil is 2000 turns times 1 meter per turn, gives 2000 meters or 2 kilometers. The total resistance of the coil equals the total length times the resistance of the wire per kilometer, which equals 2 kilometers times 20 ohms, gives you 40 ohms. The power consumption is I squared R, which is 1 amp squared times 40 ohms, gives you 40 watts. So the voltage required is V equals I times R equals 1 amp times 40 ohms, which is 40 volts, and the current is just 1 amp. Require a power supply capable of delivering 40 volts minimum and 1 amp minimum. Magnetism. A current carrying conductor produces a magnetic field around the wire as shown in the picture. Even in a vacuum, a magnetic field is produced. The magnetic field strength is called H. Each circular line represents the strength of the magnetic field H, and it gets weaker the further away it is from the wire. At any distance from the wire, H times L equals the I, the current, where L is the circumference, the path length around the wire at H, and I is the electric current. It can be made up of many current segments, or I is the electric current. It can be made up of many current segments or turns, then I becomes Ni. For example, H4 is weaker than H3, and H3 is weaker than H2, but H4L4 equals H3L3 equals H2L2, which equals the current I. Flux is the amount of magnetism or magnetic current flowing through an area A, and B is its density. So B, the flux density, is flux over area. B is defined as the magnetic flux density. In air or vacuum, H is related to B by a factor called mu naught, called the permeability of air. The B field of air, B air, is mu naught H. In a magnetic material, a core, the H field is amplified many times relative to the B field of air. This relative factor between a magnetic material and air is called mu R. The B field of a magnetic material is expressed as B core equals mu R times mu naught times H, or mu H, where mu equals mu R times mu naught. UR is not a constant value, as H is increased because the material starts to saturate at certain H value. Therefore, a BH curve is used to determine the B for a certain H value. Since H equals Ni over L, H is expressed as ampere turns per meter, or A-T over meters. Here's an example of a BH curve. This is the type of core we're going to use, steel 1008. You can see for at magnetic density B of 1 Tesla, you go across, you come down, and gives you about 300 amperes per meter. So B equals mu H, use the BH curve. So mu equals mu naught UR. For air, B air equals mu naught H. At 1 Tesla, this is for air, H equals Ni over L, which is 800,000 ampere turns per meter, or 800 ampere turns per millimeter. For steel 1008, the B core UH at 1 Tesla, H equals 300 ampere turns per meter, mu naught equals 4 pi times 10 to the minus 7. Okay, so you can replace there's an example of air. You can produce a flux density between two magnets. You can also replace the permanent magnet with a current carrying coil, which is an electromagnet. In air gap, B field equals mu naught H. The unit of B is in Tesla, T. Require that H and I over L to produce a magnetic flux density of 1000 air gap is 800 ampere turns per millimeter. Example to size up a coil. If the air gap is 3 millimeters and you want B to be 1.2 Tesla in the air gap, so H equals 800 times 1.2 times 3, which gives you 2888 ampere turns. We could construct a coil with 2880 turns with 1 amp per turn. Note that the required NL for the core is ignored since it represents a very small percentage of the total Ni over L, because the relative permeability mu r of the core is several thousand times greater than that of mu naught of air. It can be easily adjusted later if necessary. Okay, magnetic field around a conductor. The magnetic field, which is the blue circle, produced by a current carrying conductor, is around the conductor. If we have 4 conductors each carrying the same current in the same direction, in between the conductor field cancel. These are the red dots here. They cancel. Around the outside of the conductors, they add up. So the field is 4 times the field of one conductor. A solid hollow cylinder with a current coming out of the page produces also a circular magnetic field around it. Inside the hollow, you notice the current directions are in opposite. So the magnetic field inside the dotted red lines cancel. They are in opposite direction. So, and this is a segmented hollow cylinder showing 4 segments. The current direction in all 4 segments is out of the page. And basically no difference between a solid hollow cylinder and a segmented hollow cylinder in producing a magnetic field. A conductor inside of a core produces a strong magnetic field, B field, the blue line. In the core, very weak field in the air. The field in the core is several thousand times greater than the field in the air. Magnetic field or B field blue produced by 4 conductors is similar to a single conductor. No magnetic field inside basically. And if you add an inner core, the field inside the inner core is cancelled. It still produces the same field on the outside. Current on a solid disk. The dotted blue line is the magnetic field underneath the disk. The current direction in the disk is black. The magnetic field blue produced by the current in the disk. No difference in the magnetic fields between a solid disk and a segmented disk. Magnetic field B field, the red color, and produced by a permanent magnet. Notice that the magnetic field direction produced by the disk current blue is orthogonal at 90 degrees to the B field. Also notice that the dotted blue line is the magnetic field underneath the disk. So they produces 2 fields, one going counterclockwise and the dotted line is clockwise underneath. And again, there's no difference between a segmented one and the solid one. Electromagnetism. The right hand grip rule. Current flowing in a wire produces a magnetic field around the wire as per the right hand grip rule. It does not matter if the current is constant or changing. Note that the field and the current are orthogonal to each other, i.e. the field vectors and the current vectors are at 90 degrees to each other. There is a way of representing the diagram on the left is by having a current vector going straight up parallel to the page, a field vector out of the page, because on this side here it's coming out of the page. On this side here is going into the page, and this is how we would represent on a diagram. A changing magnetic field vector induces a voltage, which in turn a current in a wire wrapped around the magnetic field vector as per the left hand grip rule, LHGR. The magnetic field must be changing, either increasing or decreasing. Magnetic field constant or not changing does not induce a voltage. So this is the difference between the right hand grip rule and the left hand grip rule. For a field vector, you need to be changing. If it's constant, it will not produce a voltage. Also notice that a field decreasing is equivalent to a field increasing in the opposite direction. Note that the field and the current are orthogonal, i.e. the field vectors and the current vectors are 90 degrees to each other. So a representation of the diagram on the left will be a field vector parallel to the page pointing upwards, and there's the current vector into the page and the current vector out of the page. Note, field decreasing is equivalent to field increasing in the opposite direction. Okay, so we have a field vector here that's decreasing on the left side and increasing on the right side. So the decreasing one is equivalent as a field vector increasing downwards, and they induce a voltage both from plus to minus in the same direction. It's similar. This is similar to a coil surrounding a conductor, which induces a voltage. Applying the left-hand grip rule on the decreasing magnetic field B field vector on the left-hand side of the conductor induces voltage into the page. Applying the left-hand grip rule on the increasing magnetic B field vector on the right side of the conductor also induces voltage into the page. Note, field decreasing is equivalent to field increasing in the opposite direction. Note that the field and current are orthogonal, i.e. the field vectors and the current vectors are 90 degrees to each other. So field vector parallel to the page, field vector also parallel to the page but upwards. This is the voltage occurring vector into the page. So this will be the same thing if the black one is a field vector, it's increasing downwards, and if you have a coil wrapped around it will induce a voltage or a current shown by the red arrows. Okay, generate a right hand rule. Mechanical energy directly to electrical energy. So the thumb points in the direction the wire moves, or the force. The index finger points into the magnetic field, and I is the induced current. So a generator, you apply a magnetic field, which is your index finger. You apply a force or a motion, which is your thumb, and the result is an induced current, which is the electric energy you get out. So there's another representation shown between the magnets. Your thumb is pointing in the direction of force, your index finger in the direction of the magnetic field, and you get the middle finger points in the direction of the current. Motor left-hand rule. So for motor is a device that converts electrical energy directly to mechanical energy. So you use your left hand for the motor and you use the right hand for the generator. All three components are orthogonal to each other. For a motor, you apply a magnetic field, and you apply a current, and your thumb will point where the force. You get force, mechanical energy. The magnetic field of the conductor, red arrow. And then this diagram here shows you a conductor inside of a magnetic field. And the field produced by the permanent magnets is shown by the black arrows. The magnetic field of the conductor, red arrows, and the magnetic field of the magnet, black arrows, at the left of the conductor, which is equivalent to higher pressure or a source, and the magnetic field of the conductor and the magnetic field of the magnet subtract at the right of the conductor, which causes a lower pressure or equivalent to a sink. And here where the fields add up, on the other side the fields cancel, and you get a force on that direction. So here are the two formulas. That's all the two formulas you're gonna ever need. And one formula is for the generator, the other formula is for the motor and thruster. So this is for a cylinder, we'll talk more about later, but the voltage is BWLR, and I normalized to 1.88 volts per turn or segment. This is when the the flux density is at 1 Tesla, the speed is at 1800 RPM, the length is at 100 millimeters, and the radius is at 100 millimeters. So the force is IBL, normalized to 1 Newton per amp. Force per current equals BL. So B is at 1 Tesla, L is at 1 meter. V is induced voltage per wire turn or segment in volts V. B is the magnetic flux density in Tesla, T, sometimes referred to as the B field. W is the rotational speed in RPM, revolutions per minute. L is the length of the cylinder in millimeters. R is the radius of the cylinder in millimeters. Note that VBWRR is for two circular surfaces, or V equals BWRL and L equals R to maintain the cylinder outer surface area as the same as the two-end circular surface. We'll discuss more about that later. F is the force in newtons. B is the external magnetic B field in Tesla, T. L is the length of the conductor carrying the current in meters, and I is the current in amperes, amps. Okay, so basically the current, the magnetic field, and the force, they must be orthogonal to each other. So we use the left hand rule for motor and the right hand rule for generators. So the way the three of them are orthogonal is one has to be circle, the other one has to be radial, and the third one has to be straight. So here's a graphical representation. Here's the circular, and from the center vector, this is the radial component, and the arrow showing the dot is straight out of the page. This is the straight component, this is the radial component, and the circular component. At the point where the arrow meets is a tangent. A tangent to a point on the circle is at 90 degrees to the radius at that point. So generator, again, you apply magnetic field, you apply force, and you get current, electrical energy. The thrust and motor, you apply magnetic field, you apply current, you get force, you get mechanical energy. For the motor, it's circular, and for thrust, it's straight, the force. For a generator, F must be circular, for both, generator or motor, the force is circular. This is the choice that we choose. You can have either cylindrical or you can have disc, but this is the preferred choice. I is straight and B is radial. If you're using a disc, B is radial, I is radial. Electromagnetic thrust, F must be straight. I is circular and B is radial. Or you can have B circular, I radial. This would be like equivalent to two counter circulating fields inside a toroidal coil. So here's the basic motor or generator. You have one coil loop. There's a magnetic field from the north side to the south side of a permanent magnet. When an electromagnet is used to replace the permanent magnet, the magnet is called the B field coil. Or we can also, you don't need to just add one loop, we can add multiple loops. When we add multiple turns to this coil, this one loop, then it becomes the induction coil. This device can operate either as a motor or as a generator. Both effects exist simultaneously. When operating as a motor, the generator effect opposes the motor effect. It's called the back EMF. You want to create a generator that has the generator effect but no motor effect. We want to create a motor that has the motor effect but no generator effect. can such a device be created? Here is an example. This machine can only operate as a motor. As a motor, the current in the conductor produces a magnetic field, red, this magnetic field, which interacts with the magnetic field, black, resulting in a force, blue, causing a clockwise rotation. The current flows into the page on two conductors and out of the page on the other two conductors. So you see in each case the force is circular or 90 degrees, so it causes a rotation. As a generator is like, now if you try to operate this as a generator, think of this as like a bar magnet and a conductor moving together with a bar magnet. As a generator, it's like a bar magnet moving together with a conductor, therefore no voltage induced. It cannot operate as a generator. V-core. In the diagrams, I represent the coil as an envelope. The envelope is the cross-sectional area taken up by the coil. The total current is expressed as ampere turns. For example, in a cut core on the right, H is the height, W is the width, and L is the mean length, circumference of the coil. For example, 100 ampere turns and H equals W equals 10 millimeters. The total current is 100 ampere turns. It can be a single turn at 100 amps. It can be 10 turns at 10 amps for each turn. It can be 100 turns at 1 amp for each turn. If 1 millimeter by 1 millimeter wire is chosen for the 100 turns, the envelope is 10 millimeters by 10 millimeters, 10 wires by 10 wires, which is equal to 100 wires, which is the cross-sectional area of the coil. So if you take an electromagnet, which is a coil, is represented by a band around the core, which is just, I just showed the envelope. So the B-phi coil is defined as, this is the coil that produces the B magnetic field, or just simply called the B field. Induction coil, this is the main coil where the motion of this coil cutting the B field induces a voltage, internal current in the induction coil. So homopolar generator. Homopolar or Faraday effect